Hey guys, sorry for the later than expected post. I had to finish up some grading for the progress report before I had a chance to record the video. Sorry about missing today. So just quickly, for the do now, this was just again practicing how to write the polynomials in factored form given the zeros. So if I'm giving you these zeros, again, we spoke about this in the last session. In order to write these polynomials in factored form, you're going to group them as binomials, and it's always going to be the opposite of whatever the given zero is. So for number one, for instance, again, feel free to pause it if you want to practice them on your own, but I'm just going to go through these quickly. Excuse me. But for number one here, it would be x, and instead of 7, I would put minus 7. It's always the opposite. And again, it's always a binomial. The next one will be x. Again, you can use whatever variable you want. I tend to always use x. And the opposite of a negative 3 is a plus 3. And then we have a positive 8. So that binomial will be x minus 8. And then again, we'll set it equal to 0. That would be this in factored form. For the next one, number 2, given these zeros or roots, solutions, however it's written, how you would write this in factored form. Again, it's going to be binomials. Since there's 3, there'll be 3 of them. And it'll be the opposite again. So it'll be x. And the opposite of 4 would be negative 4. X. The opposite of negative 2 is a positive 2. X. The opposite of negative 5 is a plus 5. And then for our last one here with 2 and negative 2, again, we'll have 2 since there's only 2 zeros this time. And the opposite of positive 2 is negative 2. And the opposite of negative 2 is positive 2. Again, the reason when we write it in the binomial factored or factored form, it's the opposite, goes back to when we were solving the quadratics. When we were solving the quadratics, once we got it down to its factored form, let's say we had something like x minus 7, x plus 8 equals 0. Once we got it into the factored form, in order to solve it, we set the separate binomials equal to 0. So we did x minus 7 equals 0, and we did x plus 8 equals 0. Then we solve them. Plus 7 here, we end up with x equals 7. We solve here, we end up with x equals negative 8. So these solutions always ended up being the opposite of what they started off in the factored form. So that's kind of how we know that if we have a solution already, when we put it back in factored form, it's the opposite. All right. So the other thing we're going to look at, we're just going to look at a few of the graphs. The new topic for today is going to be how to deal with imaginary solutions or non-real solutions. But we just want to focus on a few more graphs. Maybe go over. This is one from the homework that we'll go over. The homework check was posted for you guys to still hand in. But from these homework check problems, this was one of the packets, one of the graphs, just to again go through this and just to go through what you'll be expected to be able to do. So from this graph, the end behavior is up, up. Is it even or odd degree? We should know it's even. Again, you know it's even from that table. If it's in the same direction, the end behavior, it's always even. The leading coefficient is going to be a positive. And again, we know that because it's up, up. Whenever it's up, up, that's when the leading coefficient was a positive. Again, we're not going to be talking about any relative maxes and mins at this time. And then it says the zeros and their multiplicity. So again, our zeros here are going to be negative 3, negative 1. Again, our zeros are our x-intercepts at all times, 1 and 3. And all of these have a multiplicity of 1. Again, we spoke about the different multiplicities our last session. It was in the last video, as a matter of fact, and how to know when it has a multiplicity that's not 1. If it passes straight through, it's 1. If it's something like this here for number 1, if you see this dot there, that's going to be cubic. Whenever it like lingers at that value, it doesn't just pass straight through. And whenever we have a u at the intercept, that will be when it has a double multiplicity or 2 times. Anyway, these are the zeros, and then we would write it in factored form. Again, factored form, what we just talked about, it would be x plus 3, x plus 1, because it's opposite, opposite, x minus 1, it's the opposite, and then x minus 3. And again, we'll put it's equal to 0. In our other packet, we'll look at, this is the packet that said polynomial graphs and their multiplicity. This was posted on our last session. And this is page 10. And I just want to go through a few of these graphing examples as far as what you should do, what you should expect. Excuse me. So in class today, we went through about 4 of these, so we'll go through about 4 of them. This is the graph of the function, and I'm asking you for the zeros and their multiplicity. Let me zoom in a bit more on this. So for the zeros and their multiplicities, for a, this is going to be -2, 1, and 3. Those are the zeros. All of those zeros are passing straight through, so they all have a multiplicity of 1. Again, if they have a multiplicity of 1, that's the default. You do not have to write anything. That's understood. Now, the next thing asks you about the leading coefficient. It says the degree and the leading coefficient. Now, again, from the graph, all I'm going to want you to indicate really is whether it's even or odd degree. You don't have to give me a specific number. But based on the in behavior here being down and up, I should know that this is odd. Again, if it goes in different directions for in behavior, then it is odd. And when it's down up, again, if you look back at the table with the in behavior, if it's down and up, our leading coefficient is positive. That's the default. Left and right in behavior, again, we already wrote that. It's going to be down, up. Again, down is negative infinity, up is positive infinity. And then it says to write in factored form. So again, writing this in factored form would be x plus 2, the opposite of the -2. X minus 1, the opposite of a positive 1. And I'm going to write underneath because of space. X minus 3, the opposite of the positive 3. And then that would all be equal to 0. Again, ideally it should all be in one line. All right, I'm going to move down to the next one. For the next example, number 2. For this one, I need to know my zeros. The first column here asks you for the zeros and their multiplicity. So for this one, number 2, I'm just going to zoom in on the picture a little more so you all can see the multiplicity here. I'm sorry, the zeros here. For this one, my zeros are -2 and 1. Here we are at -2. Here we are at 1. Hopefully everyone recognizes that these have a multiplicity of 2. You can write mult2, you can write 2 times. Something needs to be written indicating that it has a multiplicity of 2. So both of these have a u at that value, meaning it's a multiplicity of 2. So the next question said the degree and the leading coefficient. So the degree here, because they're both going in the same direction, I know it's even. So it's even degree. And then since it's down, down, I know that my leading coefficient had to be negative. C asks me for the in behavior. The in behavior is down, down. Again, negative infinity for down. And then D asks me to write this in factored form. So writing this in factored form. Now, because I know my leading coefficient is negative, I'm going to put a minus in front because I know it's going to have to end up being negative. Minus. And then I'm going to put A for some reason. Then I'm going to put x. Again, in factored form, it's always pointing to the wrong thing. In factored form is always the opposite of the solution. So it's going to be x plus 2. And because it has a multiplicity of 2, I'm going to put squared. And then I have x minus 1, because it was a plus 1 here. And again, it has a multiplicity of 2, so I'm going to put squared equals 0. All right. I'll do number 4, and that'll be our last one here. For number 4, this one, first thing asks you for the zeros. So again, let me zoom in a little bit more on the picture so you can determine the zeros. The zeros for 4 are going to be here at -2 and here at 1. Again, the multiplicity is always going to be a piece of that question if it has a multiplicity or not. So for -2, hopefully you realize that this one lingers. It doesn't just go straight through. Again, if it passed straight through, it would just be like that. Or, something like this, whatever. But it would go straight through. In this case, it lingers a little bit there at that -2. So because it lingers there, that's when it has a multiplicity of 3. And then for the 1, that's a u. So that also has a multiplicity, but the multiplicity there is 2 whenever it's that u. The degree here is the next question. It's down and it's up. So as long as it's in different directions, it is odd degree. And if it's down then up, it's going to be positive for that leading coefficient. And we already said the end behavior was down up. Again, down is negative infinity, up is positive infinity. Sorry for all the movement. And then for D, the last thing asks you to write it in factored form. So writing this in factored form would be, again, as long as it's positive, it's not wrong to put a plus sign, but it's not going to be necessary if it's a positive. So as long as it's positive, don't have to worry about that. It's going to be x plus 2, because again, that's the opposite of that, -2. And it has a multiplicity of 3. A multiplicity of 3 means to the third power. And then it's going to be x minus 1, because again, it's the opposite of the positive one. And that has a multiplicity of 2, so it'll be to the second power, equal to 0. All right, going to move down to the next page. And on the next page here, this is page 11, the multiplicity packet. We're going to look at like the first 3 here, and we're going to practice actually sketching the graphs. That's what we're going to be moving towards, actually graphing these polynomials. So this will be our first step towards the graphing, or the sketching. It says sketch a possible graph of each of the following functions on the axis provided. Pay attention to the zeros of the function, making sure the graph behaves appropriately, yada yada. So, for this, excuse me, what you want to ask yourself as you approach each problem is what's the degree first. So if we look at A, how would you determine the degree from this form? You determine the degree because this is the first power, this is the first power, this is the first power. So the 1, the 1, the 1 means this is third degree, basically, or odd. If it is odd, this doesn't have a negative a or a negative leading coefficient, so we're going to go with it being a positive leading coefficient. So that means that our end behavior is going to be down, up. So we have to keep that in mind when we sketch the graph. We need to make sure it's down on this side, up on that side. Obviously, that's not sufficient yet, but that has to be met. Now, it also tells us the zeros. By it being in factored form like this, it's giving us the zeros. Now, if you quickly look at it, you might do the following. You might put 2, -1, -3. If you do that, you are going to be incorrect. Because again, This is the factored form. These are not the actual zeros. The actual zeros are going to be the opposites, because we would have said x plus 2 equals 0, yada yada. So our actual zeros are not 2, 1, etc. It's going to be, oops, sorry. The actual zeros are going to be these opposites. They're going to be negative 2, 1, and plus 3, plus 1, plus 3. So that's where we should have our points on the axis. Negative 2, positive 1, and 3. So now we have to get ourselves a sketch that's going to be down on this side, up on this side, and it has to pass through these values. All that in between stuff doesn't matter. What you will notice that there will be some examples that you'll see. These do not have it, so obviously for these, don't worry about it. But you will have some values where I'll tell you what the y-intercept is. So for instance, if I told you the y-intercept was 5, you would need to take that into consideration as you were doing your sketch. For these examples here on this page, you don't have any y-intercepts, so that's not going to be an important piece. All you need to do is worry about the end behavior and the zeros. So it's going to be something that looks like that. It's got the 3 zeros, it's odd, it's down, up. That would be a sufficient sketch. Let's look to B. For B, we again look at this. It's a 1, it's a 1, it's a 1. So this would be odd degree, because the 1, 1, 1 is 3. And for this one, there's no negative in the front, so that means it's a positive leading coefficient. Since there's a positive leading coefficient and it's odd, we need our end behavior to go down and then up. The zeros that we get from this are going to be negative 1, and positive 2. So negative 1, positive 2. Hopefully you guys recognize that the negative 1 happens twice. They wrote it 2 separate times, but you could have also written this as x plus 1 squared. So just understand that this has a multiplicity of 2. Either writing it twice like that, or again, it could have been written with the squared there. You need to be comfortable with seeing it different ways. For different problems, it can be expressed either way. So remember what it means to have that multiplicity of 2. You need to remember that the multiplicity of 2 means that it's going to look like that when we get to that value. That multiplicity of 3 is going to look like that when we get to the value. So keep that in mind. So negative 1 is going to be a u. It's got to be down, up. And then it's got, so let's go ahead and do ourselves a sketch. Let me color here. So it's going to be down. I got to make sure I go like that. Again, I had to make a u at the negative 1 because it had a multiplicity of 2, so it couldn't cross. And then it has to end up going back up through the 2. Our next example, C. For C, our 2 zeros, we have 2 zeros for this one. It's going to be negative 2, and then this is plus 2, plus 2. So this has a multiplicity of 2, and this also has a multiplicity of 2. So 2, negative 2. Now this is 1, 1, 1, 1, which is 4th degree. So therefore it's even. And there's no negative in front here, so it's even and it's positive. Since it's even and it's positive, we need end behavior to go up, up. And both of these, have a multiplicity of 2, so we're going to be making u's at these values. This is an example of how your sketch could look. It has to start up. Something like that. It has to be up for both. And again, it's going to be a U shape for both of those zeros. All right, last question here will be D. For D, for this one, when we go through and figure this out, it's going to be 1, 1, 1, 1, which means it's fourth degree, which means it's even. There's nothing indicating it's a negative, so it's going to be up, up. For this one, my zeros are going to be -3, and it's going to be +1. +1 has a multiplicity of 3. So here we go at +1, here we go at -3. Now I need to do my sketch. I need to be up, up. And I need to remember that at this one value, I'm going to have to look like this multiplicity of 3 where it kind of lingers. So I'm going to try to do that side first just to try to make sure I get it right on that side. So over here, I'm going to start up because I have to start up. That's not the best. I'm going to do a little better than that. Too far over. Could be something like that. It's not the best, but you get it. It should look something like a lingering third degree and then go back up. So this would be an example of what this would look like. All right, so I'm going to go back to my note sheet and finish up what we're going to do today. All right, so the other piece of what we needed to cover today was when we have non-real solutions. So everything we looked at so far are real solutions, whether it crosses the x-intercept, 7, 3, 5, etc. So when we think about non-real solutions, we have to start thinking about those imaginary numbers. So those imaginary numbers are going to be things like I, our square root of -25, which is 5i. It could also be, like a -3i. But remember, to be not real, it could also be what we called a complex number. And those complex numbers were those combinations where it was a constant and an imaginary number. So it could have been something like 6 minus 3i. Something like, -2 plus 4i, etc. These would be examples of complex numbers. Now, when they are not real solutions, things are going to change a little bit. And this is when we're going to use this theorem. It's called the fundamental theorem of algebra. Fundamental theorem of algebra. What this theorem says is the following. If a polynomial has a non-real solution, then its conjugate is also a solution to the polynomial. This is the fundamental theorem of algebra. So, let me explain. So, first of all, again, I just alluded to what it means to be non-real. These are these things involving those imaginary numbers, those numbers that don't actually exist, so we have the square root of a negative. But if we do have these imaginary numbers or these imaginary solutions. It's important that you remember what it meant to be the conjugate. We spoke about the conjugate when we were covering the imaginary numbers with the quadratics chapter. So let me just refresh your memory on what the conjugate is, and then we'll allude to how that's going to be important here. So first of all, what the conjugate is when it's the opposite of the imaginary term. So in case you forgot, let me just give you a quick reminder of what that is. So if your solution is I, the conjugate, so let me just actually leave myself a little bit more space here. I'm going to say here, this is the imaginary number. And then on this side, we'll do the conjugate. So, for instance, if I gave you just I as my complex number, the conjugate of I is going to be negative I. It's just the opposite of the imaginary term. So it's going to be negative I. If I gave you 7I, then the opposite of 7I would be negative 7I. If I gave you negative 3I, the opposite of negative 3I would be positive 3I. So the conjugate is the opposite of the imaginary term. Now, these are just a single imaginary term. What's also going to be considered a non-real solution will be if we have a complex number. A complex number, remember, is when we have a combination of a constant and an imaginary term. So it could be something like 2 plus 3i. The conjugate of 2 plus 3i is going to be 2. That doesn't change. It's only the opposite of the imaginary term. So the 2 is still the same because that's not the imaginary term. But it will be a minus 3i. Next, let's say I have negative 8 plus 7i. The conjugate of that is going to be negative 8. Again, the negative 8 is not the imaginary term, it's the constant. And then the 7i would become a minus 7i. That's the one that is the opposite. And then let's do one other one. Let's say 3 minus 5i. And the conjugate of that would be 3 stays the same. Again, only the imaginary term changes sign, plus 5i. Now remember, when we were working with these, the purpose of this was to basically the only reason we really were multiplying by the conjugate was to get rid of the I term, aka the radical, in the denominator. So that's when we use this. So what is this telling us? So what this is telling us is the following, that if we have, so I'm going to give you, the following. I'm going to say that's the solutions. So I'm just going to say write in factored form. I'm not going to write it out for everyone. Write it in factored form, given the zeros. All right, so our first example, I'm going to tell you that the zeros are, let's go with 3, negative 7, and I'm going to give you 8i. So 3 and negative 7 are real numbers. So there's nothing different in regards to the 3 or the -7. So we're going to approach that the same way we did before. So writing that in factored form, it's always just going to be the opposite. So it'll be x minus 3. Again, still the binomial, still the opposite. And then it'll be x plus 7. Now, the thing that's different is the fact that now we have a non-real solution. So when it's a non-real solution, we're going to write x. So you could see it as, minus the 8i, because that's the original. But the other one, so this is telling us that if it's a non-real solution, then its conjugate is also a solution. So that means not only is 8i a solution, but negative 8i is a solution. So we would have x minus 8i and x plus 8i. And again, we would still put that equal to 0. That would be this answer in factored form. So example 2. For example 2, let me give you these zeros. Let's say I have negative 3i, 9, and 7. And I want you to, again, write this in factored form. So if I have to write this in factored form, I'm again going to start with the regular numbers first, the real numbers. So if I'm starting with the real numbers first, again, I'm always doing a binomial, and it's always the opposite. So this is going to be x minus 9, and this is going to be x minus 7. Now, the fundamental theorem of algebra told us that if there's any imaginary roots, that the conjugate is also a solution or also a root. So this is what I have, negative 3i. So I know that plus 3i is also a root. So then I'm going to have x minus 3i, x plus 3i equals 0. Next example, for this one, let me give you guys one with a complex number. So for this one, I'm going to give you 2. And then my other two roots, let's say, are 7 minus 3i and negative 2 plus 4i. All right, so for this one, these are my zeros. So again, this tells us that if an imaginary number is the solution, then its conjugate is a solution. So I need to think about what's the conjugate of this. The conjugate of 7 minus 3i is going to be 7 plus 3i. The conjugate of negative 2 plus 4i is negative 2 minus 4i. Again, the only thing that changes sign is the I term, not the constant. So now when I'm writing this in factored form, it's going to be x minus 2. It's always the opposite. And it's going to be x minus. You could put this in parentheses. It's up to you. You don't have to. You could do 7 minus 3i. Or you can just say x minus 7. You don't necessarily need the extra set of parentheses. But the 7 has to be the opposite still, just like the 2 is the opposite. So the 7 is still going to be the opposite. So it's going to be minus 7, and then it's going to be minus 3i, x minus 7, and then it's going to be plus 3i. And then again, we would put again x. This time it's going to be the opposite of the 2, so it's going to be plus 2 plus 4i. And it'll be x. And then it's going to be x plus 2 minus 4i. Again, I put one with parentheses, one without, just so you could, see how it looks with or without it. Either way, it's fine, because the plus and the minus are going to both end up being there anyway. But again, you still have to change the sign of that first number, because that's always the opposite when you're putting it into the polynomial. All right, and the next ones, I'll do one more and then I'll go to the couple at the bottom. For number 4 here, for number 4, let me give you 3 minus 5i, and I'll give you 2i. So again, this fundamental theorem of algebra tells us that if we have imaginary roots, that their conjugate is also a root or also a solution. So if we have 3 minus 5i that works, then we know that 3 plus 5i works, because that's the conjugate. 2i works, so negative 2i works. And then we would go ahead and write that out in the factored form. Factored form would be x minus, again, we always do the opposite of like this constant here. So it's going to be minus 3 minus 5i, and then it will be x minus 3 plus 5i. And then we'll have x minus 2i, x plus 2i. Okay, I have 2 examples here. I think I have 3 actually, yeah. So I have 3 examples here. I'll give you, you guys pause your video, try to see if you can figure these out, check them out, try them on your own before unpausing and checking the answers. All right, so here are my answers to 3 and 4. Hopefully everyone was able to get these with relative ease. Again, the use of the parentheses for number 4 is not necessary. Again, you can use them, you don't have to. Most of the time I will not use them, to be honest, but just wanted you to be clear on what was being plugged in. This would be plus 2i. So I just did it with it in this set, without it in the second set. Either way is perfectly fine. And I just wanted to do one last question here for number 5. For number 5, for this problem, excuse me, I just wanted to just kind of use this to show you guys why this fundamental theorem of algebra is relevant, or why, why it's used. And I'll explain that quickly here. If you were trying to solve this, you would have went backwards. You would have distributed the x times x gives us x squared. X times negative 3i is negative 3ix. Then I would have distributed the 3i again. 3i times x is it's positive 3ix. And then 3i times a negative 3i is going to be negative 9i squared. Now, that's equal to 0. In solving this, you'll realize that these will cancel. I'll end up with x squared. And then everyone should know what I squared is. At this point, I squared is negative 1. So what we're plugging in is going to be x squared minus 9 times negative 1. 9 times negative 1 ends up being positive 9. So we end up with x squared plus 9 equals 0. If I wanted to solve this, I would minus the 9. And I'd end up with x squared equals a negative 9. At this point, to solve this, I would square root it. And I would end up with x equals plus or minus 3i. Because the square root of that negative 9 would be the 3i. And we always, when we take the square root, need the plus or minus. So this is kind of, obviously, with the conjugate, it's a little trickier. It's a little bit harder to do the math on. But this is where that comes from. And this is why you would never just have the 1i. It could never just be the 3i without the negative 3i being an option. So this is pretty much it. You guys are good to go. You should be clear enough to do the homework and everything at this point. Have a great day. I'll see you guys on Friday.